Morning, everybody. We're just going to give it a few more minutes here, wait for a few more attendees to come in, and then we'll get started.
Hey, Leslie. Leslie.
Okay, we'll get things kicked off. Thanks, everybody, for taking some time today to attend our webinar on ASHRAE 62.1, Understanding the Indoor Air Quality Procedure. Some of the names on here I do recognize. I'm Mike Lett. I'm the Vice President of Marketing for the Odell HVAC Group, and we're really excited today to have Tim Boyd with us. Tim is the Regional Vice President for GPS Air in Charlotte, North Carolina. Licensed professional engineer with more than 25 years of experience and has in-depth knowledge in designing and building commercial mechanical and control systems specifically focused on healthcare and complex commercial applications. He spent many years working with national field service business on the understanding of service reliability and preventative maintenance solutions. And today, in addition to supporting the Northeast, Canada, and Latin American territories, Tim handles corporate relationships with large commercial customers on developing and supporting strategic solutions geared to support their sustainable energy initiatives. So please welcome Tim Boyd. Over to you, Tim. Thanks.
Great. Thank you, Mike. Hi, everybody. I'm going to share my screen now, and we're going to get into the conversation around the recent changes of 62.1.
And just quickly before you start, Tim, if there are questions, comments as we go along, please put them in the chat, and we'll make sure to address them at the end. Thanks very much.
Appreciate it. Thanks. Yeah, feel free to add as much questions as possible. I love this conversation because I think it's been very interesting. As I go around and talk to engineers throughout the U.S. and in Canada, what has been very clear is that this has been a long overdue and awaited change within the 62.1 category for ventilation. To kind of set some context for this, the indoor air quality procedure has been in the code for quite some time, actually probably since about 1981. But of recently, the standard has began to update back in 2019 and then 2022, and then obviously has been codified into your province's building codes going forward. And the changes were really around this idea about how do we create better ventilation efficiency systems or more efficient systems, largely principally around the idea of energy reduction, building decarbonization, electrification needs, and so on. And so all of these concepts kind of coalesce within the 62.1 category and really focus on what's known as the indoor air quality procedure. So we'll get into the indoor air quality procedure, but at the high level here in the macro conversation, what ASHRAE is trying to do is provide you a tool in an effort to utilize a way in which you can help reduce the carbon footprint of your buildings, lower your energy cost, as well as, if done correctly, you can also lower your first cost, and quite significantly too. And so I'll pepper in some stories and some examples as we go through this course today. This is the agenda. You'll see kind of as we walk through this, I'm going to start with how it gets into a code and what the procedural elements are. Then we'll get into the differences between the ventilation rate procedure and the indoor air quality procedure. I'll talk about some of the calculators, or at least the calculator that ASHRAE created for this context. And then we'll kind of wrap up with a handful of different notary conversations that are ancillary to this conversation today. So diving in, codes and standards. As many of you know, the code ASHRAE typically creates a standard that gets reviewed by your province and then gets codified into the code at some point, a year, 2 years, 3 years later. Oftentimes, this is what it would look like. So I'm showing you an example of the IMC 2021 right here. And in most part, they're almost all identical from what I've seen. There's a few minor changes that kind of elaborate. But effectively, when you go look at your local code, they tell you the outdoor air that's required is typically the minimum outdoor air flow rate shall be determined in accordance with, and that 403.3 in this case is the VRP. But there's always an exception. And the exception states where the registered design professional demonstrates that an engineered ventilation system design will prevent the maximum concentration of contaminants from exceeding that obtainable by the rate of outdoor air ventilation determined in accordance with the VRP, the minimum required rate of outdoor air shall be reduced in accordance with engineered system design. So this opens the avenue of that ventilation rate table was designed not to be the lowest possible ventilation strategy if you could in fact create a better indoor air quality solution in the space through other means, principally through filtered air and so on. As a corollary to this, if you go look at your energy code, typically the mechanical ventilation of the energy code actually asks for you to provide the outdoor air in its lowest rate. And I'm not saying exactly the way it says it, but if you read it, you'll see what they're looking for is the most efficient ventilation strategy in an effort to also meet your energy code. So when you dive into the procedures, what you'll notice is that there's actually 3 procedures in 62.1. The ventilation rate procedure, that's the table that you guys are probably very familiar with, where you fall down to a category, and across the category will give you outdoor air per person, plus outdoor air requirements per square footage. And then you always divide by what they call an E sub Z, ventilation effectiveness. That gives you a pretty prescriptive approach, and I'll get into some details there, but that's the ventilation rate procedure. The indoor air quality procedure is traditionally more of an engineered approach, meaning you have to design some aspect of the system in an effort to create the air quality that you're looking for. But that requires a lot of risk on the engineer to kind of determine some aspects about what's the generation rate in the space, what are the contaminants you're trying to prevent from being too dense in that space, and so on. And so what has changed is that the ventilation rate procedure, the indoor air quality procedure has become more prescriptive. It's actually, they've standardized it, removed the risk from the engineer. They've also removed the risk from the OEM so that you can just simply apply the standard. And if you apply the standard using the indoor air quality procedure, you qualify. The third procedure is the natural ventilation rate procedure. That's when you just bring in outdoor air through opening windows and the like. We're not going to discuss that procedure. We're just going to discuss the top 2. And so the last piece to understand here is, as you read the standard, what you'll notice is you do not have to carte blanche the entire building for one procedure. You can actually do it by zone. And this opens up the avenue of when would the zone outdoor ventilation calculation be more appropriate under the indoor air quality procedure versus the ventilation rate procedure. And you'll see this as in examples as we walk through it. If you were to open up the 62.1 2019 user manual, you'll notice this exact statement. The VRP, or the ventilation rate procedure, is an indirect solution to achieving acceptable IAQ. The IAQP is a more direct approach to the goal. And so the question you can ask when you read this is, what do they mean that it's an indirect solution? And what do they mean that it's a more direct solution? And the answer is, if you look at the way the ventilation rate procedure table works, it actually assumes a worst case scenario inside these spaces. And so you're sizing this equipment in a very large way, such that you're diluting the contaminants in that space. And I think you would agree with that. There are instances when you have when the ventilation load is driving the size of that equipment, and you're going back to your architect and saying, look, this is how much air I'm required to bring in based on this ventilation rate table. You know, it's a very big load. Conversely to that, if you think about the indoor air quality procedure as a manner that's scrubbing that air, you would agree it's more direct. You're actually pulling these contaminants out of the air, whether it's a particulate or a gas. The corresponding system is a much smaller system, much less outdoor air, and thereby more cost effective. You get better air quality for pulling those contaminants out of the air versus just simply diluting them. And again, as I mentioned, if you do it correctly, you actually, with what you're installing, will be far less than what you're removing, thereby getting first cost savings as well. And that's the approach. That's why you can see here that they actually prefer this approach. They just needed to make some changes in the code so that you get the benefits, you get the better cleaned air, but you also get it with the decarbonization. So let's now kind of talk to the differences on the energy side of this. Quite simply, the ventilation rate procedure is a very large outdoor air procedure. As I mentioned, it's dilutive. And you would agree that the energy use goes up as you bring in more outdoor air. And so larger systems require a lot of energy for running those systems, as well as the installed cost. In the indoor air quality procedure, you would design your outdoor air such that you're managing to the pressurization of that building, right? That's always fundamentally key. You want to positively pressurize your building. Then you want to add in anything that you might require for exfiltration needs, whether you're turning on an exhaust fan for a bathroom or a kitchen. Those are all important to include in outdoor air. Then you can, instead of doing the ventilation rate procedure for what's your ventilation outdoor air, you can actually look at, can I do it in a cleaned air approach instead? And if done properly, you get similar, if not better, air quality with a much more prescriptive and reliable energy use for your system. This is so fundamental that even the US GBC under LEED 4.1 and now LEED 5.0 has adopted this procedure. And that's to kind of to demonstrate how fundamental this has been in the shift within the 62.1 code. So at a high level, you'll see here, I'm just showing you what changes happened or how it lived in 2016 and now how it lives today, both in 2019 and later. But notice you have to design under the indoor air quality procedure. You as the engineer or designer would have to figure out, well, what are my design compounds? What are the limits? What are the generation rates? So on. Today, they've standardized all that with a calculator. And so ASHRAE took all the research, all their understanding, and built it into a calculator that you can download for a small fee. And you can run, based on those activities, what are the generation rates and compound limits and so on to see, does this system work? And then us as the manufacturer are able to build you solutions that actually just meet the standard. And so now you just apply the standard, you work with an OEM who can build to that standard, and it's a much simpler approach and much more prescriptive. And so very, very easy to use. I've included the changes in 2019, and then these are the changes in 2022. I'm not going to go through them, a little bit didactic, but for your purposes, when we send this out, you'll have that. So if you want to go through what actually changed, you have that in your archive. But what I do want to walk through is the workflow. So notice there's 6 steps through the workflow in 62.1. And regardless of what procedure you go through, whether it's the IOQP or the VRP, it's the same. It's still 6 steps. They haven't changed that process. So what feels very prescriptive in the VRP and might seem like, oh, I got to run a calculator in the IOQP is actually very, very simple when you compare them side by side. So let's step through those. So step 1 is you have to do an outdoor air quality measurement. So what they ask you to do is go to the regional air quality website. So if you're doing a job in the US, you would look at what's known as the NAAQS table under the US EPA. Similarly, in Canada, where you guys are, you can look at the ccme.ca table. It's the air quality table there. What that does is that gives you what are the contaminants outdoors in your local region that you'll be bringing in. So what are the pollutants coming into your space that you have to manage for? Secondly, as you all do, you go do a survey, right? You go to a site and you walk a site. Part of your survey is looking around the building, outside of the scope of that building that you're designing, to see what are other issues that you have to contend with. So for instance, I got a call yesterday. There's a factory that's doing food processing. And unfortunately, locally, there's a waste water treatment plant that's effluent air is coming into their outdoor air system. That's, those are the types of challenges that you might not see on a weather station, but you would see locally if you do that site walk through. And then lastly, obviously, you document all that. So you document what you see, you put that in your notes that as you send it in for review. Second is this step 2 is systems and equipment. So the basis of what you need and 5.5 is you need a MERV 8. That's fundamental. You got to, as a background, you need that background. You need a MERV 8 that passes the 52.2 test or ISO EPM 10 test. Either way, it's a single pass test that demonstrates what's the efficiency of that rating such that it meets the MERV 8 requirement. There's also an air cleaning device aspect to this. So if you're adding any air cleaners into your system, they're required to meet the no ozone certification known as UL 2998. That's pretty standard. You're bringing in natural ozone outdoors. You just don't want to add any additional ozone to the air as you're trying to clean it or sanitize it. And then similarly, 5.9.2 is the ultraviolet devices. They also can produce ozone. And so there's a requirement that they do not transmit 185 nanometer wavelengths, such that you can also eliminate the ozone there as well. And then the last two, 5.18.1 and 0.2, they really speak to the control strategy, simply that the control strategy meets your minimum ventilation design and strokes accordingly and the like. So those are all things that you guys probably are very aware of. Now you step into the procedures. And again, this is where it kind of branches. You go into the ventilation rate procedure, the indoor air quality procedure, in accordance with the space or the zone that you're looking to design. Notice, though, that there's 6.1.4. I point this out because most people miss it. And what it says is if the national standard exceeds the requirements of the outdoor air that you're seeing, or is if the national standard inside is actually less or lower than what you see outdoors, you are required to go to a higher MERV rating. What do I mean by that? So the US EPA just updated their design limit. It was 12 micrograms per cubic meter. They just updated to 9 micrograms per cubic meter. So now all those cities where outdoor air effluence is between 9 and 12, they're required now to add a MERV 11 as the free filter for any outdoor air that they're bringing in. A little bit more expensive for those cities that have dirtier air, but obviously makes some sense there. Similarly, there's an 8-hour ozone limit. So if the 8-hour ozone limit exceeds 0.1 ppm, you're required to add an ozone air cleaner in the space or in the airstream to manage that as well. Now you can get into the ventilation rate procedure. I'm going to assume most people, if not all, are familiar with this calculation. So I don't want to belabor the point here, but let's look down at the bottom. So what our example today is going to be is a classroom. And so notice the outdoor air requirement in the VRP is 10 CFM a person. The square footage requirement is 0.12 CFM a square feet. And you can see the occupant density is either 25 kids or 35 kids. We're going to do an example with 25 kids. And we're going to assume an E sub Z of 0.8. That's effectively a high supply, high return setup. So a traditional setup in that space. If you run through that calculation, where you multiply the CFM times the number of people plus the square footage times the square footage of the space, we're assuming 1,000 square feet, you divide it by 0.8, you end up with 462.5 CFM or 18.5 CFM a person. Okay, so please remember that number, 18.5 CFM a person. We're going to come back to that as an example between the benefits you see in the indoor air quality procedure. So now if you go down into 6.3 under 62.1, you could see where they start to define how do you manage the indoor air quality procedure. And you notice what they've stated here is in the last sentence, I'll just read it. For each design compound, NPM 2.5, the emission rates from the indoor sources from occupants, building materials, furnishings, equipment, and other sources, and the outdoor concentration shall be determined. What does that mean? That means all sources that create, whether it be a VOC, a gas in the air, or particulates, have to be accounted for. And that way you can design a system that can manage those, right? Pretty simple in that regard, but trying to get that information was difficult historically. This is now what you'll see when you open up the standard. they've actually now defined the compounds, they've defined the design limits, and they define the cognitive authorities. Moreover, they've also added into the calculator what those generation rates for each of these, depending on the category. So now everything's done for you. All you got to do is say, I'm doing a school, and they immediately say, this is your generation rate for 25 people. This is the generation rate for the building. And you now have all the generation rates you need, both outdoor particulates and inside the spaces. That's key. That now really simplifies this entire process. And I'll show you the calculator here at the end. If you look at these design compounds, I just want to point out a few things. So notice, start from the bottom where you see ozone, carbon monoxide, and PM2.5. Notice PM2.5 is 12 micrograms per cubic meter, right? I mentioned now that it's being updated to 9, and ASHRAE just updated an addendum to 9. So when that gets codified, our systems have to now require to 9 versus 12. But to the point, PM2.5, carbon monoxide, and ozone, that is outdoor air, right? So that's all the pollutants coming in that they want you to measure from the outdoors. Scroll up to the formaldehyde. You notice the limit there is 33 micrograms per cubic meter. That is principally off-gassing from buildings. Those are your glues, from carpets, your wall, your paintings from the wall, your cardboard, so on. All aspects of furnitures, ceilings, paints, construction materials will off-gas formaldehyde. Okay. The other design compounds you see, those are VOCs principally coming from human occupants in the room. And so now if you think about this, you actually have the ability to manage all the building off-gassing, all the pollutants coming in from outdoors, as well as the occupants in the room. That's the full scope of it. And then the last item there on the bottom is ammonia. That's for animal facilities. And so now you even have that ability as well to understand what are those design limits for these general spaces that you're being asked to manage to. The second aspect of the calculator, which does this for you, I'm just showing it to you so you understand it, is this idea of a mixtures of compounds test. So there are compounds in the air that target the same human systems. So for instance, look at eye irritant. Formaldehyde and ozone both target eye irritant. So as well as xylene and acetone and acetaldehyde. But what you're required to do, if you look at that calculation, is you're required just to add up all the ratios of what your compound is compared to the design limit, and then add those together. And that ratio has to be less than 1. Basically, you can't exceed the design limits in total. I'll show you that in the calculator. That will make some sense. But effectively, you can understand what this is principally, but know that the calculator just does it for you, and it'll give you a passing score if appropriate. Okay, now for those of you who like math, I want to show you what the mass balance analysis actually looks like. What is the actual calculation that the calculator is doing? So take a look at the bottom left. You'll see two very similar diagrams. The difference is one is a VAV and the other is a constant volume. So for our example in the classroom, we're going to assume a constant volume solution with the filter position A. Okay, that now leads to the right side where you can scroll down to filter position A, constant volume, and you'll see two calculations, right? Two equations. For reference, the ASHRAE calculator looks at the right equation, the C sub BZ. C sub BZ stands for the concentration in the breathing zone. And so what they look at is they look at what are all the contaminants for each of those contaminants you got to analyze, and then what's all your cleaning capacity on the bottom, right? That's in the denominator there. We'll blow this up in a second. But recognize that what's added differently here, what's added between this one and the equation above it, is an air cleaner. So not only are you looking at the contaminants and what outdoor air can offer you, you're also looking at what does an air cleaner offer me. Thereby, I can lessen the outdoor air load in doing this. Notice if you look at the one that says filter none, that calculation is the VRP calculation. And so the only thing is the VOZ that's required that you're using, which is outdoor air. Hence, when you go to filter location A, C sub BZ equation, you'll notice there's more cleaning capacity loaded into the bottom to help handle the contaminants on the numerator. And so for that reason, the air cleaner was an important aspect to the upgrade. And so what did they upgrade? They already had the 52.2 test. That's that single pass particulate test. What they added was the requirement for ASHRAE 145.2. So they built a standard that does a single pass gas phase test. This is a third-party test that can be done in multiple different third-party laboratories, where you can actually test what is the single pass of your carbon filter, molecular filter, what have you, that now handles those specific contaminants that are in the standard and in the code now. There's also some other tests you can run. They all principally point back to the 145.2. I will tell you C, D, and E, those are tests that you can develop and then you submit to your authority, your AHJ, for approval. But for the fundamental, for most engineers that are looking at this, 145.2 and 5222 is what I would recommend you put in your spec to make sure that what you're specifying to meet clean air meets those two requirements. And so now, as I mentioned, OEMs can just build equipment, right? And so now there's this simplicity of, hey, I just got to meet these two tests, and I got to make sure, and I got to manage it in a way that can actually tell you if it's going, what it's going to clean in a single pass. A lot of this was informed by these two position documents that ASHRAE wrote over the course of 15 years. They've been updating this. But notice they're identical, but I'm going to get into what is the efficacy that's listed here, and then what is the safety that's listed in these tests, in these documents. So first, let's talk about the efficacy. The filter efficiency, E sub F, right, requires what is the single pass efficiency for each of those compounds. And notice, this is what you would get. You get a report that had this type of information in it from the OEM for the product that you're looking to incorporate into your design. And it would demonstrate, this is my single pass efficiency for particulates, that's your 52.2 test. And then everything else is, quite frankly, the 145.2 test. So you can see how important that 145.2 is. And so now plug that into your E sub F, and you'll notice we highlighted the E sub F here on your screen. Notice where that sits. The higher the E sub F, also the higher the V, the volume of air that you're recirculating through your air cleaner, the less capacity load you need on the outdoor air, right? You see that ability, that E sub F is very important, and thus giving you the what you need fundamentally, so you can now start to lower your outdoor air. And if your outdoor air is highly pollutant, I'm going to blow this up a little bit here. If your outdoor air is highly pollutant, you'll notice the VOZ not only exists on the denominator, it exists on the numerator as well. And so for cities that have a lot of outdoor pollutants, you also, by lowering your outdoor air, you also improve, not just, you improve the numerator, and then you add in clean air, now you improve both aspects of this equation. And so that's why you can get really good savings doing this approach. I'll give you a good example. Traditionally, you can in most traditional places, especially high occupancy public assembly spaces, you can cut your air by about 50% outdoor air with the right air cleaner. And your cost savings could be somewhere between $1 for every $1 you invest, you're saving about $8 off of that project in first cost. That's the value of this thing, of this type of benefit for so many different reasons. So now understanding this equation, I'm going to blow it up one more. I'm going to just highlight this, but notice you run the equation, the calculator runs the equation for each component, right? So it runs the equation, N is the contaminant in the space for, acetone and benzene and formaldehyde and so on. So it goes down each time and runs that equation to find out what is the concentration in the breathing zone for each of those contaminants. And then it divides it all by the cleaning capacity. So how much outdoor air you're bringing, how much cleaned air you're bringing, and what's the effectiveness of that particular component. And then notice the E sub Z, that's your 0.8 in this case. The 0.8 is the high supply, high return. So changing the way in which you're sweeping that room, whether high supply, high return, or low supply, high return, or what have you, changes also and adds value to getting a better concentration in the breathing zone. This now highlights what I was talking about. So this is really the blow up, and this is for you. So when we send this to you, you can kind of look at it and study it a little bit more. But just notice the recirculated airflow through the air cleaner plus the filter efficiency gives you what you're looking for. That's the fundamental change in the equation for managing the what an air cleaner can do for managing the air quality. All right, so now I want to go through the safety features just quickly. So inside that position document I mentioned, there were two aspects: efficacy, which I just walked through, and now safety. There were really three tests that they outlined, and these tests for the air cleaner actually lives inside standard 241. So if you're interested, we can talk about, we did a standard 241 conversations about a month ago now with Odell. If you're interested, you have that recording, but the test they point back to 241 to say, what is a proper air cleaner? What should it look like? And so they look at several things in safety, in the safety category. The first thing they look at, and we've already mentioned, is that it should not create any additional ozone. So it has to have a certification or a labeling known as UL 299A. The second certification or test that you have to run and prove is what's called a no additional chemistry or air chemistry test. And the way they run that test is they take some limonene, that's that lemon and lime scent that's in a lot of your cleaning products. They take about a capful of that, it's 10 milliliters, and they evaporate that in a very big space. And then they run the air cleaner. If the air cleaner is creating any ozone or any other reactants, it will react with the limonene. So limonene by itself is innocuous, but in the presence of ozone and other highly reactants, it will fragment and create formaldehyde. And formaldehyde, as we know, is a carcinogen. And so that's the test. That's the second test. There's no additional air chemistry. And then the third test that it has to pass is a no additional particulate test. It's a clean lab test. So you set up a clean lab, you rate that clean lab, so class 4, class 5. And then as you run the test, if that product is reacting or adding anything into the air, it's going to fail that test. Effectively, the clean lab requirement, you can go one level above, but you can't go 2 levels above. So if you set it up for a clean lab class 5, the test can gravitate up to a class 6, but it can't go above that to a class 7. That would be a fail. Okay. So if you think about it, if you have an air cleaner that is safe in that it creates no additional ozone, creates no additional air chemistry, creates no additional particles, and it's highly effective, I think you would agree you now have a really good air cleaner that you can apply and lower your outdoor air and get very good air, extremely low cost, and hopefully save a lot of money off of those tight budgets that you guys are dealing with. The last test here is the verification test. Effectively, there's an air quality canister systems test. It's pretty cheap. You put it in the space, it measures it for 8 hours, kind of while you're commissioning. This is normally when you would do it. And you just prove that the space meets is below the design limit. They recently just updated table 7.1, kind of immaterial what they did, but to the point, what I'm showing you here is not exactly, if you see the addendum that came out last week. So I can get into that in some more detail if interested, but to the point, you still need an air quality system to test it. Okay, so that's the standard. A lot of information. Hopefully that was helpful and gave you guys some really good detail. Now comes the fun part. It's just the calculator. So now you just quickly enter everything. You don't have to worry about all that back end, but I think you now have a good understanding of, hey, is this a good opportunity for me to replace outdoor air with cleaned air and get the benefits that we just talked about? And so I want to talk through this in practice and show you what it looks like. So this is the calculator. I'm not showing you all the screens of it, but what we want to do is walk through that example, that 1,000 classroom with 25 people, and recognize that other OEMs, ourselves included, we offer you a free calculator. And so that calculator will do this exact same thing and should give you the exact same answer. Ours, in fact, does. But effectively, all you're doing is that mass balance calculation. So if you remember that calculator I told you to remember for VRP, right? I think it was 18.5 CFM a person. Now let's do that exact same analysis, but this time let's do 5 CFM a person of outdoor air, and let's add in an air cleaner that could do 250 CFM using that table I showed you. Okay, so that table we plugged into this calculation of single pass efficiency. And what you'll notice is that 5 CFM a person and a 250 CFM air cleaner for that 1,000 square foot classroom with 25 kids in it passes. And notice on the bottom, the mixtures test gives you those fractions that I talked about. As long as they're less than 1, you pass. That's an enormous, that's huge. Think about it. So let's talk about what the value of this is. First, I want to go into first cost. So notice that top line there. That's that classroom example we've been walking through. You're saving 337 CFM. That's approximately, if I use just the enthalpy of 40, That's approximately 3 tons of savings. And considering where you are, if you're in inner city Toronto or inner city Ottawa, or if you're, maybe out on the outskirts, your cost per tonnage of install might change, right? So you might be at 3,000 or you might be at 5,000, depending on where you are. But let's just take inner city Toronto. That's probably a more difficult place to install equipment. So let's just say it's about $4,000 a ton. You're looking at somewhere around $10,000 to $12,000 of savings for that for that savings per classroom, right? Per classroom. So now you start looking at this across the spectrum of how many classrooms are in that space, and what you see is, wow, I can get a lot of savings. As an example, I'm doing a job right now in the Brooklyn market, Brooklyn, New York, and you can imagine they have a lot of struggles with if they're trying to retrofit a building. This is a great application where you can't get more air into the space, or the existing ductwork was designed under an older code, and the cost to upgrade that would have been exorbitant, right? More bigger ductwork, so on. A lot of renovation work would have had to be done. In that particular example, we were able to take a ton off of every classroom, or half a ton, depending on the space where it existed in relationship to the southern exposure. But between that, the gymnasium, the cafeteria, we're looking at between 50 to 70 tons removed from that 3-story building. That gives you an idea of how big this could be. Looking at a lecture hall, this is probably these are the biggest areas of savings you'll see, is large public spaces assembly. Typically, public spaces of assembly, the ventilation load is what's driving the size of that equipment. And so you can traditionally take anywhere between 10, 15 to 20 tons right off the bat and save a lot of headache on cost as well as operating cost. And so notice in this example, again, we just took it right from the VRP table, the category. So it's 2,000 square feet, 300 people in that space. Again, high supply, high return. You're saving about 14 tons. And again, if it's at that $4,000 a ton, you're somewhere in that $50,000 of savings from that piece of equipment that you were going to install. I'll give you a really good example of this one. So in the Toronto market, there was a theater that was being expanded. The engineer was trying to figure out how to utilize the existing dunnage, how to utilize the existing roof penetrations, and basically was coming up zero, coming up empty. The DOAS equipment was just getting way too big for the dunnage. The electrical needs were getting big. Obviously, the penetrations for the ductwork weren't going to work. The Odell rep actually walked in and had the conversation about what we can offer, and they were able to keep that DOAS as the same size and replace it with cleaned air instead. And so that additional that savings was quite significant, you can imagine. And I've done this in a lot of different places. And historically, you're just seeing, orders of magnitude of $100,000, $50,000. In one case, we've saved over $500,000 in, depending on the size of the building and the way that building's categorized, simply from being able to pull that tonnage off the building and replace it with clean air. Quite significant. Last one here is office space. Notice 5,000 square feet. So probably not dissimilar to the types of spaces you guys work in every day. And again, between about 4 tons can come off that space. For the market you live in, you also get an enormous heating savings here. We're not showing the heating, but I'm showing this in tonnage, obviously. But think about your heating savings. If you can lower that outdoor air, you lessen the preheat requirement. You also improve the mixed air temperature. You improve the humidity during the winter. So all those benefits are also added and not shown here as a first cost savings or an overall benefit to the air quality. The operating cost of this is also quite significant. So again, taking that one classroom, you're saving about 10 kilowatt hours per CFM, and at a rate of somewhere between, let's call it 15 cents to 20 cents in your market, you'll probably save around $500 to $600 per space, per classroom. I just walked another facility up near you guys in the upper state New York market, and the local energy company is offering credits of 25 cents a kW. And this particular building that we looked at, it's an 8-story building, a commercial building that needed a lot of renovations. But we were able to offer them potentially a credit of $375,000 because of the kW saved. Again, significant savings if done correctly. Notice again, the lecture hall, you can see the savings there. Call it, just strike a line around $2,000 a year in savings. And then office space, something similar. In the Toronto market, your savings here actually gets even larger because of the heating loads. And so you swap heating loads for cooling loads, obviously, but you will see either similar, if not higher, savings on the operating side. Last is a conversation that I'm sure you guys probably put in the chat. Okay, well, what about CO2? Notice CO2 hasn't been talked about. If you read the ASHRAE position document, what you'll find is that they don't consider CO2 a good proxy for air quality. Why? Well, in part because CO2 is only a determinant for people occupancy. If you recall, the way the design compounds are laid out, what they're actually looking at are more than just people. What is the off-gassing of the building? What are the pollutants coming in from the space in addition to the people that are in that space? And this is even more fundamentally key to understand. When you run through the calculation and you see those, what the pollutants are, create like first ones that are causing the you to add more clean air or add more outdoor air when you do the calculation, it's almost, I'm going to say 90%, but fundamentally formaldehyde and PM 2.5 are the first ones to pop. They're the first ones to create problems. Basically, building off-gassing and outdoor pollutants, not people. And so this really is foundational to understand. Carbon dioxide historically has been used as a proxy or as something to kind of determine air quality. ASHRAE has debunked that and said it is not a good indicator of air quality. Now they've recognized that there's a lot of confusion in the marketplace. And so as you see in that first bullet, it's commonly misinterpreted within the HVAC industry. And there's a lot more that they want to continue to inform and educate in this space. So I'm excited to see what they're going to do. But what they have done, if you drop your eyes down to the second last bullet, is they updated the addendum on that ventilation chart. And so we could talk through that, or you can reach out to me afterwards and I can give you some examples. But effectively, rather than just looking at some flat ppm that doesn't make any sense, they've actually raised and lowered, depending on that type of spaces, for the ppm to fluctuate a little bit if you were to go through the ventilation rate strategy. If you go through the indoor air quality procedure, you don't need to worry about this. You don't have to worry about opening and closing the outdoor air damper. Why? Because if you're managing to the contaminants, do you need to worry about the CO2? And the answer is fundamentally no. Notice the last bullet. There's a study done by the U.S. Navy for the submariners in those vessels, and what they found was there was no significant difference in their decision making or their performance, even as high as CO2s of 15,000 ppm when the contaminants were already handled. And so that really kind of demonstrates that it's a proxy gas, it's not or a tracer gas, it's not a real fundamental air quality issue. That aside, the NIOSH level is around 5,000. So 5,000 for over an 8-hour period is what most people agree to not to go above. But that's far higher than what you would probably used to in the designs that you were either learned on or that you've tried to design to, with very high levels of, or very low levels of CO2 that require very high levels of outdoor air. This kind of switches that and kind of puts that on its head and says, look, you don't need to do that. And to substantiate this, I'm pointing to an article that came out last year. There's actually been another article that came out in December. I need to update this my deck here to talk to it. But this article here is called the IAQ Paradigm. And then he talks about it as the next generation. Max, ASHRAE fellow within the ASHRAE community. He's also was the chairman of ASHRAE 241. That was the standard I mentioned earlier that put air cleaners into 241 so you can understand what safety looked like when you specify an air cleaner. But notice what he says: source reduction and air cleaning can greatly reduce the contaminant harm without increasing ventilation rates, thus saving energy. He then goes through a history of the indoor air quality procedure, and he actually talks about the fact that it used to be, when they first launched it, it was a 4 CFM per person rate. Remember, I did our test at 5 CFM per person, right? A whole 25% higher. And yet when you do the VRP today, you're at 18.5 CFM per person. You're way higher. So he admits it's gotten out of control. And so he concludes with the combination of source control, ventilation, and air cleaning is the most practical way to handle the contaminants of concern. Effectively layer these in, right? Don't fundamentally just shut your outdoor air damper. I'm not asking you to do that. What I'm telling you is there is a more efficient ventilation strategy when you use the indoor air quality procedure. And lastly here is around what I already mentioned, the USGBC. So because of these changes, the USGBC actually adopted or points to ASHRAE 621-2022 and approves the indoor air quality procedure for your version 5 designs or higher. This is huge. You can get points for those of you who are doing lead designs. I'm working with a group in Boston right now who's looking at how they get all these additional points. They only do green building designs. And I can send this to you, we've actually been published in the US Green Building magazine. And so we have an article out there that I can ask Odell to post or send, but effectively supporting this idea of how do you build good green buildings and still provide really good air quality. Overall, if you think about, you step back and you look at a building, you get a lot of initial savings here. If you can lower your tonnage, lower your heating loads, I think you all agree you have smaller, simpler HVAC designs. Smaller air handling units, smaller chiller plants, smaller boiler plants, those can be a reality in your design. So if you're struggling to meet a budget, or if you have a job on your desk right now that's requiring bioengineering, or if you're getting into a job that was designed in an old code and you're trying to bring it up, or you're just looking to help meet the local city's electrification needs or decarbonization needs, this is a really good strategy to use. Notice you can simplify the designs. If you do the indoor air quality procedure, you don't need to be worrying about control strategies for the DCB. Those are only under the BRP side. They're not required in the IAQP. As I mentioned, smaller duct sizes. I'll give you one more example here to conclude. A job in New Jersey had a requirement had a building, that was 18 stories tall or 20 stories tall, but the first floor was being renovated to a private school. And the louvers were above the transom door, in the transom above the door for the original design of that building. And the engineer, when they did the calculation, said, look, I'm going to need to expand that louver to bring in more outdoor air to meet the requirements for this school. And what they were going to need was either knock out a door or knock out a wall and then create this huge, loss of space in an inner city, school that they're where space is a premium. Our rep went in and said, no, you don't need to do that. We can actually clean the air and keep your existing ductwork. And so we saved them tens of thousands of dollars on that job. And we also saved the architect from having to redesign the spaces. And we gave the school back all that additional square footage. I mean, it's a win-win-win on all categories, right? That's fundamentally what you can do here with the right approach to when to use the indoor air quality procedure. There is also under the 90.1 code, I didn't go into this, I didn't show it, but the ERV is required in 90.1. If you read the ERV table though, what you'll notice is you can get below that ERV strategy and not require an ERV if the outdoor air is below a certain percentage of the supplier that you're supplying to that space. And it graduates as you go up in scale, as you know. An example there was a job that's being designed right now. It's in Michigan being designed, but it's actually for Texas. And they were going to have to provide ERVs for all the rooftop units for this big box play area, kind of like a trampoline park. We walked in, explained this to the engineers, just like I'm explaining it to you guys today. And through running the calculations, we saved them over $100,000 in the rooftops alone, let alone all the additional duct sizing and control strategies and the like. So again, significant savings. There are some other considerations, I'm not going to go into those, but I think those examples really highlight how valuable the indoor air quality procedure is and why you can see ASHRAE has really started to move this into the forefront of their methodology. If done properly, you get better cleaned air, you can lower your outdoor air, and obviously get all those cost benefits that we talked about, both on the operating and on the first cost side. So I want to thank you for your time today and for listening. I'll now open it up for questions. I'll come off the screen sharing so I can see if anybody wants to, I can see the screen and see questions and so on.
Thanks, Tim. We didn't have anything put in the chat specifically. You just see, one did just come from Mark Bedard. Can you talk about installation and operating costs for the addition of air cleaning to a design?
Yeah, no, that's proper. Thank you, Mark. So, allow me to do a plug right here, if I may. I represent a company called Smart IQ. Odell is obviously my rep. With our design, so we make a product that actually meets this requirement that we just talked about. It meets 241, and it meets 145, it meets 52.2, and it meets the new standard 62.1. That product is the one that I mentioned some of these savings. When we've done these savings, what we traditionally see is about a quarter to a third of cost for our product to get installed, and it depends on how you want to install it. So there are other products on the market, Mark, that the cost might fluctuate differently. You want to look at what's the cost of the filter to change that. Is it a proprietary filter or a commercially available filter? For reference, our filters are commercially available. How often do you have to change it? Our filters you change once a year. Some you might have to change once a month or once a quarter. And then you also want to look at how heavy the unit is, how loud the unit is, and so on. So there are various aspects to answer your question, but principally, and that's why I said if done correctly, you can save on the first cost. All of them offer good operating savings. It really comes down to some of the other benefits that the OEMs have built into their, into their solution. One of the big benefits our solution is we have a closed loop solution. So we actually monitor the air quality and we confirm for you constantly that the air quality is good. Those are some things we've added into our solution. Others, you'd have to add that in separately. But again, to your question, fundamental cost that is part of the analysis that you'd have to do. So thank you for the question. I didn't bring it up. My miss on the PDH.
Thanks, Tim. Another question came through. Are there any strategies for convincing engineers of the unimportance of CO2? ASHRAE's position is conveyed to them, but they're firm in their beliefs that it's bad for human health.
Yeah. This one's a fun one. I would tell you the strategy of trying to convince an engineer is not going to be, depending on what you're doing, is probably going to be fruitless, and you're gonna have better time finding those engineers that agree with you than trying to convince those engineers that don't agree with you. You can show them all the science, you can show them all the literature that ASHRAE punts out. Oftentimes, what most of them are telling you or tell me is that their hands are tied by their customer. And who's their customer? Oftentimes, it's the school district. And the school district would be a much harder lift to go explain to them what the real science is showing. So you might as well allow the ASHRAE to continue to educate. That being said, you can actually do, and I'll show this, feel free to reach out to Mike and set up a meeting with me. I've done this. I can run a design in the indoor air quality procedure whereby you can, I'm going to call flex the VRP. So you can actually run both in tandem such that you can make the CO2 just ever so slightly more and get your savings that you're looking to get, or even get some savings. But you make it such that if you still want to add the DCV, so the engineer is comfortable opening up the outdoor air a little bit in an effort to accommodate the, once a week when the CO2 might rise. Recognize that CO2 requirement is an 8-hour limit requirement. So it's an exposure over 8 hours. What people are fixated on is the number in an acute time period, not over an 8-hour period. So again, that's part of the education. I wouldn't worry too much about it. You'd be spending a lot of time trying to educate the market. Let ASHRAE do that. Just focus on where those that agree with you, you can give them really good design. Those that don't, hey, let's look, you can tell them to look somewhere else. Look at high occupancy spaces. Those CO2 limits don't rise when you start to do it, and you'll see really good savings. As I mentioned, most gyms, I did a gym in Chicago, 15 tons. I did a gym in Michigan, 20 tons. You're constantly seeing these types of savings.
Amazing. If there's no more questions, I guess we'll leave it at that for today. As always, Tim, an amazing job on 62.1 and the IAQP. Really appreciate your time today. It's really a pleasure to have an expert like yourself speak to this group today. So thank you so much.
Yeah,
and everybody
excellent.
who's in it. Sorry, Tim, go on.
One last thing. For those who are interested, our product, as I mentioned, you can find it at smartiq.com. We also make a calculator. If you want a training on our calculator, if you want our calculator, reach out to Odell, and we'll offer that to you guys for free. And I can show you how that works, and we can walk through some examples. Sorry, Mike.
No, fantastic point. I'm glad you brought that up, Tim. Yeah, as mentioned, please reach out to Odell. We're happy to work with you to show you just how powerful a tool Smart IAQ can be, or even have a discussion about anything 62.1 or IAQP related. So thank you again for your time today, everybody. Really appreciate it.
Pleasure. Thank you, guys. Take care.